Alrighty, folks, we are going to head. Alrighty, folks, we are going to go ahead and begin talking about forces. This entire unit is about motion and forces, and we've talked a bunch about motion. So let's go ahead and expand our conversation to discuss forces. All right, our learning target for today is I can describe what happens to the net force and motion of an object as it experiences balanced or unbalanced forces, including friction. So, we're going to really kind of focus on what is kind of net force right now, but we're going to expand upon the rest of this later on. All right, go ahead and set up your notes. Your topic for today is force, and your essential question today is what is a force? All right. Well, let's go ahead and start with this, and let's go ahead and define force. And a force is a push or a pull that acts on an object. So there are a bunch of different types of forces, and the main thing to know is that a force can cause the following things. A force can cause an object to go from rest into motion. A force can cause an object to change its speed, and a force can cause an object to change its direction. So, if you think about all of these things, this kind of relates to what we were talking about the other day with acceleration, because a change in speed, a change in direction, or going from rest into motion, all of these are examples of acceleration. So, what we know is that a force is going to cause acceleration. So, you have a bunch of different types of forces, and I've got a great little animation or GIF here of Chuck Norris doing a roundhouse kick. And what you can see is that Chuck Norris's foot is imparting force onto this gentleman in the purple plaid shirt. And that force from Chuck Norris's foot causes this gentleman to change his going or from being at rest. You can kind of see he's just standing there to all of a sudden being in motion, so much so that he goes out of the window. And so the fact that he is going from rest to motion tells us that a force was applied to him by Chuck Norris's foot. You can also see that once he goes out the window, the gentleman doesn't just keep flying in the same direction at the same speed. He actually starts going downwards towards the earth. And this is a change in direction, and that is also caused by another force, not by Chuck Norris's foot, but by gravity, because gravity is pulling him towards the earth. And so that is an example of a force as well. So, just from this beautiful clip of a roundhouse kick, you can see all types of examples of forces. All right, what is a question that the previous slide answers? All right, so how do we measure force? Well, we measure force using a unit called a Newton. And a Newton is equal to a kilogram meter per second squared. That second squared thing, that is acceleration right there. So 1 Newton equals 1 kilogram per meter per second square, or 1 kilogram meter per second squared. You can actually think of a Newton as a quarter of a pound. So if you have something that, or because in reality, weight is a force, and we'll get to that in a little bit, but a quarter of a pound is equal to 1 Newton. We also represent force using an arrow. And so if we draw something and the force is exerting, the bigger the arrow, the more force. So think about this right here, the scale that maybe you see in the produce section of your local supermarket. If you were to place something small in here, the red arrow, maybe you place like a lemon or something like that. The red arrow here, it would only go just a little bit. That's because that lemon is exerting a small force downward on this bowl. However, if you placed a watermelon in here, that red pointer would go way farther up, because that big watermelon is exerting a lot more downward force than that lemon was. And so that's going to kind of be the difference. And instead of this red arrow pointing, you can imagine a arrow pointing downwards, and the lemon has a small arrow, the watermelon has a big arrow. All right, so here's a very bad joke for you. Next time you go to McDonald's, just go ahead and order a Newton with cheese. Get it? Get it? So how many pounds of force equals 1 Newton? That's right, a quarter of a pound. Ha ha! Jokes. All right. Alrighty, folks. So let's go ahead. We talked about that scale. I want you to go ahead and take the moment to just practice this. Draw it out here, or you can draw it in your notes if you want to. But just go ahead and draw the representation of force on a scale with 1 lemon on it versus a scale with 1 watermelon on it, and kind of use that arrow to show the amount of force. So that'll kind of help you represent force well. What question do the previous slides answer? All right. So when we have forces, we can actually combine those forces together. So the net force is the overall force acting on an object after all the forces are combined. So when the forces on an object are balanced, the net force is 0 and there is not a change in an object's motion. However, when an unbalanced force acts on an object, the object accelerates. So this is when the net force is not 0. So let's go ahead and think about a game of tug of war, and we're going to kind of build on this. So imagine that you have these two teams pulling, but before that, we just have the rope sitting on the ground, okay? No one is pulling on it, therefore there's no force on the rope. The rope's not moving. All of a sudden, we have this person here come and pick up the rope and start pulling. All right, well, that person is pulling on the rope, and so the rope begins to move in the direction that this person is pulling. Well, now this person comes over and picks up the rope and starts pulling. Well, if they are pulling equally, so with equal amounts of force, then the rope is going to stop moving because this person is pulling in this direction and this person is pulling in the opposite direction. And so their net force is 0. And so the rope stops moving. Now, if this person has these 3 people join and start pulling, now you have a bunch more force pulling in this direction, and the rope once again begins to move to the right because now you have 4 people pulling versus 1, and their net force is larger than this person's net force, and so the overall net force goes in this direction. But now you have 3 other people join on this side, and so now you add their force to the net force, and the net force on this side is equal to the net force on this side, and the rope stops moving. And so you can see in a lot of different ways we can combine forces. What is a question the previous slide answers? All right, so there are a couple of different types of forces that we want to be familiar with. One is friction, and friction is a force that opposes the motion of objects that touch as they move past each other. More contact, more friction. So if you're sitting at a table or at any object, go ahead and take your hand and glide your hand over the object with just your finger touching, okay? There's not going to be a whole lot of resistance. And that's because you only have your finger touching the surface in front of you. However, if you put your entire hand down on the surface and push, you're going to notice that it's harder to move your hand than it was when you just had your finger touching. And this is because you have more objects in contact with each other. More of your hand is touching the surface. Therefore, there is more friction. So friction, more contact, more friction. Another type of force we want to be familiar with is gravity. Gravity acts downwards towards the center of the earth. And so we talked earlier with that roundhouse kick clip that the gravity was what was pulling that guy down. Everything is pulled down towards the earth, and so that is the force of gravity. Terminal velocity. So this is kind of an interesting one that combines gravity and friction. This is the speed of a falling object as it stops accelerating due to air resistance. So let's think about this. If you drop an object, the longer it drops, the faster it moves because gravity is going to pull hard or accelerates. And so after 1 second, the object will be moving 9.8 meters per second. After 2 seconds, the object will be moving 19.6 meters per second because gravity accelerates at 9.8 meters per second squared. So you would imagine, oh, well, if you drop something from high enough up, it'll just get faster and faster and faster. Well, not exactly, because air actually causes friction. Air is made up of a bunch of particles, and they aren't as strong as if you're trying to move your hand across the table, but they still have friction. And this is called air resistance. And so as you're falling and you move faster, more and more air particles are hitting you. And you're actually going to reach a point where the friction from the air particles, you're moving so fast and so many air particles are hitting you, that the friction from them counteracts the force of gravity, and you reach a maximum speed. So you don't speed up anymore. You're not slowing down necessarily, but you're not speeding up. And so at that point, the net force on you is 0. And so you reach terminal velocity. So you're still falling, but you aren't speeding up. So G force is the force of gravity. And normally we feel one force of gravity. If you're moving upwards really quickly, you're going to feel more G's or more G force. If you're moving downward very quickly, you will feel less G's. So think about if you're on a roller coaster. If you go on a roller coaster and all of a sudden, or let's say that you get to the top of a big hill and you go down the hill really, really fast, you're going to feel weightless kind of for a moment or so while you're going downhill because you're experiencing less G's. And then all of a sudden, if you pivot at the bottom and start going uphill really, really fast, you're going to feel pressed to the back of the seat of the roller coaster because now you are feeling more G's because you're moving very quickly upward. So, what is a question the previous slide answers? Alrighty, folks, to wrap up here, I want you to go ahead and watch this video that I have posted here on your Nearpod. And this does a great job of explaining G-force. This is something this is a training plane that astronauts go on in order to feel the effects of zero gravity. And they use the idea of G-force. And if you're going downwards very fast, you feel weightlessness to experience it. So go ahead and watch this video. It's pretty cool. And then we'll finish up. All right, folks, I want you to go ahead and fill out this poll on a scale of 1 to 5. How well do you understand force? Alrighty, folks. So that's it for forces. Yeah, good job.